that there's too many possibilities for a decision tree still holds. So, are there any questions on this particular version of the algorithm before we see the much more complicated version? Thank you.
Thanks, Jamie. So Jamie has to, are you stay?
Yeah.
All right, great. So this is the first quick tree algorithm, right? The one that Jamie gave. And I'm going to give a second quick tree algorithm that is much more complicated to prove the correctness. So Jamie sort of showed you everything that you need to do to show that his algorithm is correct. So it's really, it's a very nice algorithm because it's understandable that it works. The second one, it's much harder to show that it works, and the running time is also harder, but I'm still going to show it to you. But I'm going to show it to you in a picture. So the idea is that we're no longer, so Jamie's algorithm, right, it fixes x and y that it's going to pick. It's going to deterministically choose a good x and y there on different sides of the root. In the other quick tree algorithm, we're going to pick two pivots at random, x and y. And then we're going to divide the elements into three, what I'll call bags. So one bag is v of x, x is bag. That's the elements A that are more similar to x than they are to y, right? We have these pivots x and y, so these are the ones that are closest to x. Y's bag has the A that are closest to y, and then the rest is the ones where x and y are closer to each other than A. And then we'll recurse on the three bags. So here's an example. Suppose we're trying to construct this tree. We don't know that this is the right tree, but we know it exists. And for every three elements, we know which one is closer. So for example, for E and F and B, we know E and F are closer to each other than B in the tree. So that's the information we have. All right, so we choose pivots. Let's say that we choose E and we choose G. So what's going to be the bag for E? So that's all the elements that split off from G before they split off from E. So E's bag is going to be just this, right? Right? These are the ones that are closer to E than they are to G. These are closer to G than they are to E. And then this whole bunch up there, E and G are closer to each other than they are to these elements. So we pick E and G, and that makes us divide the elements into these three bags. Okay, once we have the three bags, we recurse on each of the bags. So we recurse on this one, we recurse on that one, and that tells us exactly what the tree is. Right now we only know G, H, and I are in a bag together. After the recursion, we know exactly what it looks like inside the bag. When we recurse on the rest, something more tricky goes on. So we also need to know where this thing goes, where these two go. So when we recurse on the rest, we recurse on the rest plus one node that basically represents everything in here. So that's why I say the algorithm is a little bit more complicated. It's not as clean as I think the other quick tree algorithm, which is really nice and clean. So we recurse on them, and then we combine the three trees. So we output the tree T that we obtain by putting the tree that we find here, the tree that we find here, and attaching it to this tree wherever V was in that tree. Okay, so for the analysis, I know that's already 40 minutes, so by now I assume you're tired. So I'm just going to wave my hand and say, yeah, we did it. So if the input is consistent, then we can prove that it finds the correct tree. So this algorithm does work the way it should. And for the running time, what we can show is that with probability at least 3/32, if we choose random pivots, each of the three bags contains at most 3/4 of the elements. All right. Now, what that means is that with probability at least 3/32, I'm going to be able to split my input up into roughly equal sized parts. They're not too big. So you can show that this means that you can implement the algorithm to run in order n log n time. So basically what that means is you pick two pivots, you check if this condition holds. If not, you try again. because you have this probability of having it hold, you only have to try a small number of times before this holds, and then you continue. And so that's how the algorithm works, and then it runs in n log n time, in expectation. Okay, so with that, I want to summarize so that I have a little bit of time for questions as well. So basically, this is a tale of two quick trees. Our first algorithm is a quick tree algorithm that divides the elements into two sides, right? So we pick two pivots that are on opposite sides of the roots, and we divide the elements into the left and the right subtree, and you solve it recursively. So I think that's like a nice and conceptually easy to understand algorithm. The second algorithm, a little less nice in my opinion. We pick any two pivots x and y, we divide it into three bags, one for x, one for y, and one for the rest, and then we solve the bags recursively. So it's a bit more complicated, but it gives you a better running time if the tree is not balanced. If the tree is balanced, then both algorithms give you roughly the same running time. So both algorithms are much faster than the existing algorithms, but they do need a dense input. So these algorithms only work if for every triplet, we know these two are closer to each other than that one, which I think is not that realistic. Like in actual biology applications, you're not going to have all that information. So that's future work. What if the input is not consistent? So first of all, if the input is not consistent, then our algorithm will still work. So a question is, does it come close to finding a tree that keeps as much of the branching information as possible? The second algorithm, second question is, if the input is not dense, can we still make our algorithm work? So for actual more realistic data sets, can we adapt our algorithm so that it still works and still that runs in n log n time? And that's still things we're thinking about. So with that, I want to thank you for your attention, and let me know if you have any questions.
Question?
Yes?
For the first algorithm, did you actually use, have an object actual nodes, or do you use like a list and have everything within a list to implement the tree?
Current implementation is a list, so it doesn't actually move the data around. Just throws them in the list.
I thought it was an array.
Array.
Not a linked list, I mean.
No.
So,
Yes?
yeah. What kind of problem is there in the field right now that this will solve?
So it really is this super tree construction problem.
I mean, what will that solve?
Application.
Application with what?
He's asking for real life application.
Oh yeah.
So the application is really this the thing I started with, that we want to construct these trees. So
And you know that you only know those relations.
So you only have relations for small sets. And so sometimes
Okay.
this is only for triplets, sometimes it's also for four species that you know what the relationships are, and then you need different algorithms. So
Thanks.
that's the application, yes.
And those trees unique when you end up with that.
So
If it's dense and consistent, you can prove that there's up to isomorphism a unique
Yeah.
tree.
So what I considered today was that for every triplet we're given information, then it's unique.
So
If
you-
it's not for every triplet you have information given, then it's not unique.
So if it's consistent, then the solution exists, also unique.
Right.
Yeah, I think so.
But not necessarily if you don't have information for every triplet,
Mhm.
right? I mean, you could have zero information that
Right,
any
right,
tree
sure,
would
sure,
work,
sure.
so.
Yeah.
Yes,
Have you guys tried working with a real data set?
no, not yet. So there are data sets out there that have this information, so that have information for triplets and for which you want to construct then the super tree, but those are not dense, right? The denseness assumption really is a very strong one, that for every triplet you have information. That doesn't hold in these data sets. So we first need to extend our work to deal with that before we can use actual data sets. Yes?
So if you don't have triplets to start with, and you have four, or at least four of them or something, is it a lot harder?
It's
You
a
do
lot
similar
harder,
thing, or-
it's a completely different, yeah. But people have thought about that too.
You can't like decompose those four into different triplets and then do it that way.
You
Yeah, that's a
can,
good question, you should be able to, right? So then maybe it's not harder.
well, but you have to check density and consistency after you've done that.
Yeah, actually, I need to look that up again. So I'm not 100% sure, but it sounds now like maybe that actually, yeah, you can just split it up and then you can use our algorithm and the existing algorithm as well.
Yeah, I'm just curious. So this kind of a tree, they only compare one character. I mean, if you say these two are, more similar on this, but the other two things maybe are more similar in another genetics or character. So I mean, how these three are. If you have these two characters, how do you compare their similarity then?
Yeah. So we're right now abstracting all of that away, right? So
Yeah.
we're just assuming the biologists have figured out whether this makes sense. These two are more similar than that one. However they did that, I don't know. And I don't really care anymore because now I just want to use that. But you were right. Like how is that done?
And that's why I said it's the uniqueness, because if they're similar, then you can think about getting the unique from there.
I thought the uniqueness you mentioned is if you're given such all this information, whether the solution is unique or not.
Exactly, but the dense condition is the most important one,
Oh, yeah.
right? And that's coming from the biologist, isn't it?
Like it's the assumption we need, but that I don't think the biologists are able to give us.
yeah, yeah.
Right, thank you.